Hello, my name is Vikram Jain, and this is my midterm 2 problem 4 presentation discussing how to solve problem 4 and the methods I used and the corrections I made after getting feedback back after receiving my test results. This problem gave me the most trouble during the test because it dealt with thermal energy, and thermal energy was an area that I had not touched as much upon during my studying and preparation for the exam. So the problem 4 reads, it was worth 25 points, it reads, you put a thin metal pot containing 2 kilograms of room temperature water on a hollow electric stove. You stir the water vigorously on an electric beater, which does 100 joules of work on the water every second. You observe that after 15 minutes the water reaches a temperature of 100 degrees Celsius. So already from that we can see that the delta T would be 100 minus 12, thus resulting in 88 degrees Celsius as the change in temperature. The specific heat capacity of the water is 4.2 joules times grams times C to the negative 1. What was the change in delta E thermal in the water was the first part of the problem. And to solve that, since we already know delta T is 88 degrees Celsius, we can use the equation delta E thermal equals MC delta T. And with that we can plug in the mass, which was, since it was 2 kilograms, we need to convert that to grams first. So we convert it to 2,000 grams, multiply that by the specific heat capacity given, which is 4.2, and you multiply those two quantities by 88, which was the change in temperature. Doing so gets us the result, which is the delta E thermal equaling 739,200 joules. The next problem deals with what the thermal transfer of energy Q into the water from the surroundings was. With that, we have to understand a fundamental principle about thermal energy, which is that it equals the work plus the transfer of energy, Q. So when we rearrange the equations, we can make it equal Q equals delta E thermal minus W. And we already know what delta E thermal is because we found that in part A, so we just need to find W. And W we can find by multiplying the quantities of 100 joules per second times 15 meters times 60 seconds per meter. And doing so gives us the resulting Q value when we subtract it from 739,200 joules, which was the delta E thermal. And our resulting value is 649,200 joules. For the next portion, dealt with the energy principle because it asked for the change in delta E of the surroundings. So with that, we have to understand that through the energy principle, that the delta E of the system and the delta E of the surroundings should equal 0. As a result, we can set delta E of the system equal to delta E of thermal, and delta E of the surroundings was equal to the negative quantity of the delta E of the system. As a result, we can make the delta E of the surroundings equal to negative 739,200 joules. The last portion of this problem was by far the most challenging because it gave us a twist to the scenario and of the situation that had been set up already. The pot was taken off and 2.26 kilograms of sweet potatoes were dropped in it. And with that, the initial temperature of the room temperature of the potatoes was equal to one another. Thus, the potatoes had an initial room temperature of 25 degrees Celsius, and a specific heat capacity was given for the potatoes to be 3.14 joules times quantity grams times C to the negative 1. So to determine the final temperature of the water in the sweet potatoes once they came to equilibrium, we had to understand the several key aspects of the energy principle and thermal energy. First, we have to understand that delta E equals W plus Q, as we discussed earlier in part B and C of the lab. Delta E of the thermal was set to equal 0 because because of the new situation that was in hand, in terms of that was the total quantity equaling 0. Delta E thermal of the sweet potatoes plus delta E thermal of the water was set equal to 0. As a result, when we plugged in the formulas for that, by understanding this situation, we could do the mass of the potatoes times C, which is the specific heat of the potatoes, times the change in temperature, which was T final, which is what we're looking for, minus what their initial temperature was, 25 degrees Celsius, plus we add in the delta E thermal of the H2O, which was mass of the water times the specific heat of the water times the temperature, final temperature, which, remember, since it's equilibrium, would be equal to the final temperature of the sweet potatoes, minus 100 degrees Celsius. By plugging in this equation and rearranging them, we found a result to be 65.7 degrees Celsius. The hardest part for me was understanding how to set up and approach the problem, and it required me to learn more about thermal energy and look back on what I need to know for this test in greater detail in that area and understand more about the energy principle. By looking back and doing this exercise, I was able to learn more about thermal energy as a whole and how to apply it to different situations in the future. Thank you, and this is the conclusion of my lab. This activity was very successful, and I appreciate you listening.